All right. I sent the link to everybody. I hope you can hear me. Well, I'm not sure. I think in principle you should be able to hear me and see me. All right, okay, good. So I see Bruno, Gabriel, Oscar, Ulises, Vinicius here. All right, good. So first of all, let me finish a little bit with what I was saying in the last lecture. So, to calculate beta in dimensional regularization in MS. So, first of all, we see that the bare coupling is written with respect to the renormalized one as mu to the epsilon lambda plus some ak of lambda over epsilon to the k. And but then we know the definition of beta is that beta is mu d mu of lambda when the bare objects and epsilon are constant. So let's just act with this operator. So acting here, of course, we get 0. Acting here, we get epsilon, right? Times the same bracket. Right? But then we have powers of lambda. So we have lambda here and here some function of lambda. And we know that when we act with this on lambda, we get the beta function. So here I add the beta function. And of course, here I had lambda, but in order to extract a lambda, I had to take a derivation here. So plus AK prime over epsilon k. So this is the equation for beta. But now let's consider that this beta that depends in principle on lambda and epsilon, let's write it as minus epsilon lambda plus beta tilde. And just plug in here. Well, you see, this is, so from here we get minus epsilon lambda, and here plus epsilon lambda, so that cancels. And then we get beta tilde from this term, plus A1 prime over epsilon k. Sorry, plus so just the leading terms, so the terms without epsilon would be just just one moment. So minus epsilon lambda times this means here I have epsilon to the k minus 1. So k equal 1. So A1 of lambda with the minus sign. Yeah. And here as well, epsilon times divided by epsilon to the k. Again, I have to have plus A1 lambda equal to 0. So then beta of lambda epsilon is equal to minus epsilon lambda plus beta tilde, which is A1 prime of lambda minus A1 lambda. And then taking epsilon to 0 means that beta is, so this term vanishes, and here I get A1 of lambda, but from this term I get, well, sorry, I forgot there was minus epsilon times lambda, so here there was a lambda. So A1, 1 minus, minus 1 plus lambda d lambda acting on this thing. And so you see, if I would know A1 to the A1 of lambda to all orders, I would find beta to all orders. But of course I have to calculate this order by order in perturbation theory. So the only thing I know is for a few orders. So for instance, in phi 4 in d equal 4, we've calculated already A1 being 3 lambda squared over 4 pi squared. Plus dot dot dot. So then I find that beta is this thing, 3 lambda squared over 4 pi squared plus, with a minus sign, then plus lambda dd lambda of the same thing, which just gives a factor of 2. So acting on lambda squared, lambda dd lambda gives a factor of 2, but then minus 1 gives the same 1. So plus dot dot dot. And and also we had, well, I am afraid I forgot the equation for lambda bar of t, but the equation was related to beta, and so we find that in fact, so by solving the equation we find that in fact lambda bar of t, remember t is what defines the physical momentum scale, is lambda divided by 1 minus 3 lambda over 4 pi squared log t. So that's what we call the Landau pole, meaning that for certain finite t, but very, very large, you see, this is log t, and here lambda is very small. It's 1 over 1, it's very small for 5, 4. So let's say I put it, if this is 0.1, then this would be about 100, and this about 0.3. So log t in this case would be log t, let's say about what? About 1,000, which means that t would be about e to 1,000. All right. So this is absurdly large, but finite. So it means that at some finite scale, the theory does not make sense anymore. That's one of the reasons why people are curious about QED, are curious whether QED makes sense, because of this Landau pole. So you see, in 5-4 we have the same behavior, we have the same Landau pole. So the question is, does QED make sense? We don't know. All right. Yeah, you could do the same for 3 and 6 dimensions, and then you get a plus, so there's no Landau pole. It's just asymptotically free. So, say 3 in d equal to 6. Beta is minus 7 over 4 lambda cubed over 4 pi cubed. So then to get the lambda bar is lambda bar squared is lambda squared for 1 plus 7 over 4 lambda squared 4 pi squared log t. So this is now like QCD in the sense that it runs with scale, but it becomes weaker at large t, at large momentum. So this is asymptotically free. This is like QCD. Yeah, and you can, well, actually, you can do the same thing for gamma m and gamma d. You can do the same idea that I did here. The same kind of calculation. The only thing that so the only thing that we obtained is that for gamma m, we obtained that gamma m of lambda in epsilon is when epsilon goes to 0 is lambda over 2 b1 prime of lambda. So in the same way as in the case of the beta function, to find gamma m, we only need to find b1 of lambda. So in both cases, only the coefficient of 1 over epsilon is important. That's the only thing that's important in order to find something relevant to the theory. Then, in fact, we also find a recursion relation, meaning that from B1 I can find the other ones. So this is beta of lambda B prime k of lambda plus lambda B1 prime bk. So this is a recursion relation, which means that, again, the only thing important here is there. So we had A1 of lambda for beta and B1 of lambda for gamma n. And similarly, we find that gamma d of lambda is minus lambda over 2 C1 prime lambda. So again, C1 of lambda is relevant for gamma d. So all of this means that only the 1 over epsilon pole in the counter terms are relevant. So only A1, B1, and C1 are relevant. The other ones can be found through recursion relations. All right. All right, so let's go now to today's lecture, which is about the one-loop renormalizability in QED. So, you know, can someone of you check your mic to see whether they can hear me? Because I'm talking, but I'm not sure you're hearing me. Okay, there's a text here. Apparently not. Okay. Ulysses, oh, okay. Ulysses says that I'm hearing. Okay. All right. Good. All right, so let's talk about the one loop. Renormalizability in QED. So, you know, QED is the most, the theory that has been tested most. So people think of it as the most clean theory. But on the other hand, as we saw, at some absurd scale, so I even said a little bit less there because I said the coupling being 0.1, but in fact in QED alpha is 1/137. So you get for a T of about e to 10,000, right? So a momentum scale difference that is really absurd. But nevertheless, for this one you find the lambda pole. So there is this issue that on the one hand things are very, very clean in perturbation theory, but on the other hand, if you think about the renormalization group, you see that you have potentially a problem, this lambda pole. But okay, so let's forget about the issue of the lambda pole and let's do the thing that is clean. That is, let's do one loop renormalizability in QED. So first of all, let's remember the Feynman rules. So we have G mu, the propagator is 1/k² delta mu minus 1 minus alpha k mu over k². Then for the fermion, we find fermion propagator, we find 1/I p slash plus m, that is minus I p slash plus m over p² plus m². This one has matrix indices. And then the vertex was plus I e gamma mu alpha beta, again with indices. Oh, this was all in Euclidean, and then in Minkowski we find minus I, so for G mu 0 we find minus I over k² minus I epsilon times the same thing. For SF 0 we find minus I times minus I p slash plus m over the same p² plus m² minus I epsilon. which by multiplying, this is minus p slash plus m over the same thing. And the vertex is plus e gamma mu alpha beta. Alright, so these were the Feynman rules, but an important point here is that we had the word Takahashi identities. So for the vertex, we found gamma mu, we found p mu, gamma mu alpha beta of p q1, q2, q1 was equal to e sf minus 1 of q2 minus sf minus 1 q1. And we also had, for the n photon case, k mu 1 gamma n mu 1 mu n k1 to kn equal to 0. All right, so let me look first at this one. So this, first of all, these word identities, as you remember, they were the result of gauge invariance. So gauge invariance implies these constraints on the possible endpoint functions, right? So the point is that now that we have this gauge invariance, the degree of divergence will be less than the superficial one. So superficially we had something, we just counted momenta. But now we have these constraints that involve momenta. So as a result, we will obtain a smaller degree of divergence. So let's consider the case n equal to 2 for this one, right? That means n equal to 2 means there's a p, a single p, or k, right? So the only constraint is this, right? From this one, yeah, I think I have, well, okay, so these things, so there's a delta function. So momentas, the external momenta, if you remember, are restricted by a delta function. So the external, the outgoing momenta equal to the ingoing momenta, right? So in reality, out of these n momenta, there's only n minus 1 that are variables. So in this case, for pi mu nu, we have a single momenta k. So we have a single relation of this type, but that relation of transversality means that pi mu nu is actually delta mu nu times k squared minus k nu times a function of k or k squared. Okay? So that's the only thing, because this one acts on either one of the two indices and multiplying with k, with whatever k gives 0. So the only possibility is to have this factor in front, right? But as you see, that means that you so pi mu would have a certain dimension, and now you reduce to a scalar pi that has dimension d minus 2, because I put two momenta here, right? So the same thing happens with the superficial degree of divergence. The superficial degree of divergence was basically mass dimension of the diagram, right? So that means that the effective degree of divergence of a diagram now is omega of d minus 2, right? All right, so this is for n equal to 2. But now we can see if I have the endpoint function, the endpoint vertex gamma n in the quantum effective action, then I have n constraints, right? Because really I have k mu1 acting here, but of course I also can contract with mu2 up to mu n. So I have, so for n, I have n constraints on gamma n. So here too I had two. It was k nu this, and then also k nu this is another constraint. That's why I had to pull off this dimension 2 object. So now when I will have n constraints on gamma n, I will also need to pull off a dimension n object to reduce the tensor structure of pi mu nu. So I have something that will involve k mu 1 up to k mu n, right? Something like this. So that means that now the effective degree of divergence of the diagram would be omega of d minus n. Alright? Alright. Right, so we're talking about QED. So QED in d equal to 4. And in this case, in d equal to 4, we found that omega of d was equal to 4 minus n. And so substituting this in here means that the effective degree of divergence of d is actually 4 minus 2n. Um, Now for scalars, we found that omega of d was equal to dl minus 2I. So the point was that so this was the number of loops. And then internal lines add a factor of 1 over p squared plus n squared. So that is why we had minus d times this. So the number of loops was the number of q's, which we had q, so this was this factor and this is this factor. However, for fermions, so QED has also fermions. So for fermions, the propagator is 1 over p squared plus im, which means I have to subtract only one I, not two I's. For each internal fermion line, I have to subtract one. So that means that really for QED, omega of d is dl minus 2I photon minus I fermions. Okay. All right. Now, another formula that we had, for scalars, we had that for vertices, so we have Vn vertices of for phi to the n. Then I have n lines. So n lines times the number of vertices is the total number of lines in the theory. So that corresponds to 2 internal lines, because an internal line connects 2 vertices, and plus E because an external line only connects to one vertex, right? But now for QED, we have only one kind of vertex, and the vertex is like this. There's two fermions and one photon, right? So first of all, I, the number of internal lines, is I photon plus I fermions, and E is well, and the same for E, and then the number of loops is, as you remember, the number of total internal lines, that is this thing, I photon plus I fermions, minus the V constraints of the delta function for momenta. But one of the delta functions is outside, so it's I minus V plus 1. And then we also have that so writing this kind of formula, I have to differentiate between between lines which are photon or fermions, both internal and external. So I have to write I photon plus, so 2I photon plus E photon equal to, and also 2 I fermion plus E fermion. However, a photon line, so that's because a photon line again is between two vertices, but and that's also true for a fermion line. So that's the two in here, and the E, it's also because you have external lines always connect only to a vertex. But now the possibility on the other side, here we had NVN, but N corresponds to how many lines of that type do we have? Well, for the vertex, we have two fermion lines and one photon. So for the photon, I just write V, and for the fermion, I write 2V. All right, so now you substitute I and V, I and E from these relations. So remember that we had this, and also E is equal to E photon plus E fermion. So you substitute these and these in here, and then you use these two relations, and finally then you obtain the relation that omega of V is equal to 4 minus E photon minus 3/2 E fermion. So I wrote here 4 minus n when I was thinking of n as just the, so I wrote gamma n, so I was thinking of just photons, right? External number of photons. But in general, if I have a vertex that has both photons and fermions, the result is 4 minus E photons minus 3/2 E fermions. So this was before, was the n. All right. All right, so now let's see which endpoint functions are divergent. Well, so, you know, I could say, let's say E photon can be 1, 2, 3, 4. Well, 0 no, because we're talking about gamma n. So this was for the superficial divergence for 4 minus n. But we've seen that the effective one is 4 minus 2n. So in reality, these are gone. I can have 1 minus 2n because there's this effective with 2 in here, right? So now I can have only 1 and 2. All right. But then I can have also maybe also photons and fermions. What is the possibility? Well, in this case, so without this, I had effective was this one. So if I have photons and fermions, I can write the effective is equal to 4 minus, sorry, say I have this, so minus photon minus 3/2 E fermions, right? So, so first of all, you note that the number EF must be, so EF is even, because a fermion line can never be broken, right? A fermion line always continues. So a fermion that comes in, there's always a fermion coming out. So that means this cannot be 1. It can be 2. And if it's 2, it cancels with this, is 3. So then this is only 1. Okay, so the possibility of this was, as we said, was 2 fermions plus 1 photon, and that was easy to understand. That was the vertex, right? This is the classical vertex has 2 fermions and 1 photon. And then we also noted that we have E photon with 1 or 2 external lines. Yeah, why? Sorry, the other possibility is that I have, so E photon can be 0 or 1, right? So if E photon is 1, then I still can have EF. So the possibilities then are so gamma mu alpha beta, right? That was the 2 fermions plus 1 photon, and then was 2 photons. So that is P mu nu of K. And the other possibility was 2 fermions. So that will be called, how did I call it? SF alpha beta. Okay. Right. So this is so then you can write one loop of Feynman diagrams for this. Well, what is this? This is a 1 loop with 2 external photon lines, right? This would be phi mu that actually, remember, is effectively reduced to a pipe of k squared. This is what? Well, a fermion loop. So let's say fermion, and then by putting a gluon line, by putting a gluon line connecting with the 2 vertices, we find 1 loop. And this one, well, I find 2 fermions and 1 gluon, right? So for this, I do like this, right? All right, so this is one loop, one loop, one loop. So these are the three divergences of QED. And we note already that this corrects the photon propagator. This corrects the fermion propagator. And this corrects the vertex. So we can kind of already understand that QED is renormalizable at one loop because all of we have these three divergences that correspond to the three things that we have in the action. But now let's do things in practice. Let's calculate and see what the one loop result is. So before we actually do the calculation, let's note how to deal how do we deal with matrices gamma mu in dimensional regularization in dimensions 4 minus epsilon? Well, what we'll do is we'll use a bunch of relations between gammas, and well, they can be rather easily generalized. Gamma mu is B times the identity, right? This is a sum of a mu, which is a sum. Mu is a vector index, has the components. So gamma mu is D times 1. The same we had gamma mu, gamma mu, gamma mu. This is 2 minus D times 1. We've calculated this before, and gamma mu, gamma nu, gamma mu 1, gamma mu 2, gamma nu is 4 delta mu 1, mu 2, 1 plus D minus 4 gamma mu 1, gamma mu 2, and also with 3 indices, gamma nu, gamma mu 1, gamma mu 2, gamma mu 3, gamma nu is minus 2 gamma mu 3, gamma mu 2, gamma mu 3 plus 2 minus D delta mu 1, mu 2, gamma mu 3 plus delta mu 1, mu2, mu3, gamma mu1 minus delta mu1, mu3, gamma mu2. So these are relations that depend on the dimension d. On the other hand, as we said, there's the trace, on the other hand, the trace over the indices is trickier. The trace over indices alpha. So said that mu has d components, but alpha has 4 components. So when I write gamma mu alpha beta, right? Because, as I said, the dimension of the representation of the gamma mu representation is 2 integer part of d over 2, right? So in 4 dimensions, this is 2, and then 2 to the 2 is 4, but even in 4 minus d dimension, the integer part is still 2. So it's still, this is still 2 to the 2, it's 4. So even for d equal 4 minus epsilon, this is still 4. So alpha has 4 components, which means that trace of gamma mu is still 4 delta mu, and trace gamma mu, gamma nu, gamma rho, gamma mu, gamma sigma is still 4 delta mu, delta rho sigma minus delta mu rho, delta mu sigma plus delta mu sigma, delta mu rho. So these are the identities that we're going to use. All right, so we're going to start with this one, with the photon polarization. All right, so in this case, we just put, let's say, we put here momentum P, and let's say momentum K on the lower one, and here then I have P plus K. And also the external lines for the photon has an index mu here, and here an index mu. Okay, so let's write P mu of P using the Feynman rules. There's a -1 because this is a fermion loop. Then there's the integral over the loop. Then you remember that so there are no alpha indices, there are no fermion indices, because this is a trace, this is a loop. So that means that corresponds to a trace. So I have here a trace that corresponds to what? Well, let's start with this vertex. So I have vertex, fermion, vertex, vertex, fermion propagator, vertex, fermion propagator. So let's write I, E, gamma mu. Then the fermion propagator Then I'm going against the fermion line. So now I have the fermion propagator for k, which is minus I k slash plus n over k squared plus m squared. Then I e tilde gamma nu for this vertex, and now the fermion propagator with p plus k. All right. All right, so let's expand that. So I have minus times I squared, that cancels, and then e tilde squared. So I mu p is e tilde squared. E tilde squared because E is the vertex and we're talking about d dimensions. Then the integral over, sorry, I called it k, 2 pi d. And then I had this trace, gamma mu minus I k slash plus m. Let me erase all of this. Gamma nu minus I p slash plus k slash plus n divided by k squared plus m squared p plus k squared plus m squared. All right. Yeah, and as I said, this is in d dimension, so this is e mu to epsilon over 2. All right. So we have two propagators. we have two propagators. So it's useful then to use the Feynman trick. Remember, the Feynman trick was, at least for the two propagators, was just integral 0 to 1 over q squared plus m squared plus alpha 1 minus alpha p squared squared. All right? Good. So then this is e tilde squared, sorry, e squared mu to the epsilon, then integral dd k 2 pi d. That trace that I'll not write it. But now I also have integral from 0 to 1 d alpha. It was d alpha, sorry. And then 1 over this thing, q squared. Sorry. Yeah, I had to remember that k was equal to q minus alpha p. Q mu minus alpha p. So in fact, I have to substitute already in here gamma mu minus I q slash minus alpha p slash plus m gamma nu minus I p plus k is q slash plus plus 1 minus alpha p slash plus m divided by q squared plus m squared plus alpha 1 minus alpha squared squared. Sorry, p squared. Okay, so that's our integral to do. However, now we remember, so I wrote a trace with 2 gammas, a trace with 4 gammas as a function. But remember the trace of odd number of gammas is 0. So trace gamma mu is 0, and trace gamma nu, gamma rho is also 0. So from this trace, I only keep the even number of gammas. All right. So let's see. The leading term is 1 gamma, 2, 3, 4. So that's the leading term. And in that case, I have minus I times minus I, which gives a minus. So it's trace, and let's put it outside. So minus trace, then gamma mu q slash minus alpha p slash gamma nu q slash plus 1 minus alpha p slash. So that's the leading term. Then the terms with 1m and all the other gammas is a term with 3 gammas, so that's 0. Then the other possibility is the term with both m's, so plus m squared, and then 2 gammas. And which gammas it is? Well, if I choose m, I means I choose m out of this, and I choose also m out of this, and then what's left is gamma mu and gamma nu. This is gamma mu, gamma nu, and I could write this as minus trace this, and then put the trace here. That's kind of trivial. This, remember, that was for delta mu nu. All right. Now, so let's calculate this other, this reduced trace. Now I can use Lorentz invariance. So if I would have integral dd q of q mu is 0 by Lorentz invariance. Right? That's kind of obvious, because it cannot depend on you cannot put any sorry, if here is only a function of q squared, of course. If I cannot find any other object to put the index mu on it. So we note that this numerator, has q squared and has p, but only as p squared. So this is you can treat this as a constant, right? So this numerator is of the form f of q squared. That means that from this trace, I will have to get rid of the traces with only q slash, which is gamma, let's say rho, q rho, right? If I have just q slash, that's a gamma rho q rho. So if I have only this, then since the denominator is a function of q squared, this integrated gives 0. So in here I have this, for instance, gamma mu q slash gamma mu times this thing, that's 0. Or gamma mu times alpha p slash gamma mu q slash, that's also 0. So the only two possibilities is q slash times q slash and p slash times p slash. But then we find the following. We find this trace, and the other one is with nothing. So trace, sorry, with p's, so gamma mu p slash gamma mu p slash. So both are of the same type. This is some gamma rho times q rho. And this is gamma sigma times q sigma. So this is a trace with 4 gammas, gamma mu, gamma rho, gamma mu, gamma sigma, which we found before that this was for delta mu rho, delta mu sigma, minus mu mu, delta rho sigma, plus delta 1, so mu sigma, delta rho mu, rho. And that was still multiplied by q rho q sigma. And this trace is the same thing, it's just that it's multiplied by p rho p sigma instead of q rho q sigma. So the result in the first case is then contracting with this, we get rho sigma. So this is q squared delta mu nu minus here I get q, so minus q mu q nu, and the last one I get sorry, rho sigma. Where is the rho sigma? rho sigma is so 1, 2, 2. Just one more one moment. So mu rho nu sigma minus mu nu rho sigma. Yeah, it's in the second one. Sorry. So it's q mu minus q squared delta mu nu plus q mu. So 2, right? Yeah. And I will still multiply by 4. And the other one was with p's, the other three. The other trace. All right. Now, then I had this integral this I calculated in the previous lecture. So this is 2 minus d over 2 over 4 pi d over 2 alpha 1 minus alpha e squared plus m squared 2 minus d over 2 So that's one possibility. That's in the case I have this term with just p's, or this term with just m squared. But I also have this other term. I also have these other integrals, the integral with q mu q nu, and the integral with q squared upstairs. So I have to also consider the integral with dg q 2 pi d q mu nu q mu q nu over the same thing. Now this one I will note that by Lorentz invariance, this has to be proportional to delta mu q squared. Over d, because if I multiply with delta mu, if I multiply with delta mu here, I get 1, and here I will get I get q squared, and here I also get q squared. So this is the integral of the same thing. And oh, right, sorry. Yeah. So this is q squared plus dot dot dot. And then I write this q squared, let's say 1 over d. I write this q squared as q squared plus dot 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 to make the same bracket, minus this dot dot dot, which is alpha 1 minus alpha p squared plus m squared. Right? So in the first integral, I have the integral with with a single power, and in the second I have the integral with the second power. So I mean, after some calculations, dot dot dot, which you can do yourselves, some simple algebra, you get minus delta alpha beta gamma 2 minus d over 2 over d minus 2 4 pi d over 2 times this alpha 1 minus alpha p squared plus m squared to the power 1 minus d over 2. All right. Well, so again, there's some algebra that I'll not write, where you put together all the various terms, and finally you find pi mu of p is 4e squared now we put together the same 4 pi mu squared to the epsilon over 2, so epsilon over 2, that we always put together. Then gamma of epsilon over 2, and 2 p nu minus p squared delta mu nu, and then the integral alpha 1 minus alpha over alpha 1 minus alpha p squared plus m squared epsilon over 2. Alright, so we first observe that we've obtained the same factor p nu minus p squared delta mu nu, which I said that we should obtain anyway because gauge invariance, specifically the word Hashi identities, imply that pi mu nu has this factor times something that we'll call pi of k squared. So we'll obtain this. The second observation is that we have gamma of 0, which is divergent. So gamma of epsilon over 2 is approximately to 2 over epsilon, the leading part. Then let's see, it's plus or minus, I don't remember. Minus gamma, yeah, so it's plus psi of 0, but psi of 0 gives actually gamma, minus gamma. Plus or the epsilon. And then we have to expand this thing into epsilon as well. We do as usual. We expand this as so we still have 1 alpha 1 minus alpha divided by 1 plus 2 over plus epsilon over 2 log of this bracket, which means this times 1 minus epsilon log of this bracket. All right, and this was integrated from 1 to 1 d alpha. So this term gives 1 over 6 as before, and yeah, and then the other one I can leave like this. So finally then, the result is that pi mu nu is p nu minus p squared times the leading term becomes let's see, I had the 4 times 2, so 8 e squared. Then I have this 2 over epsilon minus gamma, and then 1 over 6. And sorry, there was somewhere I forgot some numerator. There was a 4 pi squared. So 8e squared over 4 pi squared 2 over epsilon minus gamma 1 over 6 minus epsilon log of alpha 1 minus alpha e squared plus m squared. Also divided by 4 pi mu squared, since I expand this. So this is 2 over epsilon log minus epsilon over 2 log 4 pi mu squared. Epsilon over 2. And of course there was also, alpha 1 minus alpha. All right, so this is the leading term. So the leading term then, the leading term can be called, putting everything together, so I have 16 over 16 over 16, right? So then 6p squared. Yeah, so I write this as e squared 2e squared over 12 pi squared 1 over epsilon. So that's the leading term. And now I have to remember that this is supposed to renormalize the propagator. So the normal propagator for the photon in the alpha equal to 1, well, this is the alpha Feynman equal to 1 gauge, was minus delta mu del squared minus p mu, p squared minus p mu p nu. And this came to us because we had the electromagnetic kinetic term, right? So now the counter term that we get from this is minus this, so minus 2 over epsilon e squared over 12 pi squared times this thing. Okay? And this is what I call Z. This is what I called Z3 minus 1. Z3 is just notation, but it's the wave function renormalization of A, right? So it means that Z3 is 1 minus this thing, e squared over 6 pi squared epsilon. All right, I'm going very slowly, but the next one is for the fermion propagator or self-energy. So maybe right here, Z3 equal to 1 minus 6 e squared minus e squared over 6 pi squared epsilon. So this one, I'll call this sigma of P alpha beta, meaning the one point of correction. So SF would be equal to, SF minus 1 would be proportional to I P slash plus M plus sigma. So this is the correction to the inverse propagator. So by the Feynman rules, this is a loop integral. For this, let's say, call this P, and this one here I call K. Sorry. Let me denote like in my notes, like this. So this one is K, and so here I have P minus K. All right. So the indices will be alpha and beta. So this would be well, also mu. So the first would be I-E gamma mu. Then the propagator propagator with p minus k. So 1 over I p minus k slash plus n. Then I e gamma mu. This will be alpha beta. Right? So I squared is minus, then E tilde squared is E squared mu to the epsilon. Then d dk over 2 pi d. And then gamma mu, here I write as before, minus I p slash minus k slash plus m gamma mu yeah, I forgot to write also the propagator for this, which was delta mu over k squared. Right? All right, so that contracts gamma mu with gamma mu. So here I have gamma mu. But this has still fermionium. This is alpha beta. And in the denominator, k squared times p minus k squared plus m squared. All right? And as usual, we write this product of two propagators, 1 over k squared times this. I write it as integral d alpha 1 over 1 minus alpha delta 1 plus alpha delta 2 squared, and then 1 over q squared plus alpha m squared plus alpha 1 minus alpha p squared squared. Note that I have alpha m squared because one propagator is massless, the other one has mass. So previously I had m squared only. Right. What else to write? Right. So now we have this interesting this identity that I said, that gamma mu is equal to 2 minus d gamma nu. Because in here I have gamma mu, and this one, for instance, is p nu gamma nu. So I have gamma mu, gamma nu, gamma mu. So I have to use this equation. And then finally, I will be left with just an overall gamma mu. So finally, doing all that, and doing the integral over k as well. Sorry, yeah, we have to shift as well, as before k is q minus p. And there will be, since k well, there will be at some point a term is k mu, which is 0 by gauge invariance, by Lorentz invariance. Anyway, the result in the end is mu squared, mu to the epsilon, gamma of epsilon over 2 over 4 pi 2 minus epsilon over 2, then integral over alpha 2 minus epsilon 1 minus alpha minus ip slash minus 4 minus m 4 minus epsilon m alpha beta divided by alpha 1 minus alpha p squared plus alpha m squared epsilon over 2. So what can I observe now? Well, I can observe that this is not a trace now. It's something with indices alpha beta. So I cannot use trace formulas. I can only use equations like this, which reduces the number of gammas. But as a result, for instance, here I have a term with one gamma, p slash, and one with no gamma, with m. So, so now the number of gammas is both even and odd, just because there's no trace. All right, and finally then expanding in epsilon. I find that sigma of p alpha beta is e squared over 4 pi squared 2 over epsilon minus gamma minus I p slash 1 minus epsilon over 2 minus 4 minus epsilon m. Minus epsilon over 2, the same integral with the log alpha 1 minus alpha p squared plus alpha m squared, now divided also by 4 pi mu squared. So a few observations again. One is that you see both here and in the original results, well, which I erased in the propagator for the photon, we also got the same factor of e squared over 4 pi squared. That's sort of something that you will always find in loop calculations. You'll find this as a sort of loop counting. E squared over 4 pi squared will appear always. The other observation is, again, I have this log with alphas inside it that I have to integrate to obtain some finite part. What else? Yeah, that's about it. And then the divergent part is e squared over 4 pi squared 2 over epsilon minus I p slash minus 4m. All right, so what do we see now? Well, we see that this is related to the psi bar d slash psi term. So the coefficient of this divergence is related to the wave function renormalization for the fermion, right? The term that has no other parameters, but just the field himself, psi bar d slash psi. Whereas this is related to psi bar and psi. So this is related to the, once I take out the wave function renormalization, will give me the renormalization of the mass. All right, so let's do that. So let's say so the wave function, the counter term for the fermion is so the divergence here is minus I p slash times this thing. Well, if I have psi bar d slash psi, this will give me minus I p slash. So that means the coefficient of minus I p slash is the divergence that I need to cancel. So I need to put minus this thing, so minus e squared over 4 pi squared 2 over epsilon times psi bar d slash psi. And then again here m, the counter term would be minus this thing. So minus e squared over 4 pi squared 8 over epsilon psi bar psi. So that's the counter term. But then this gives me the wave function renormalization. So this was square root what I call Z2. And psi bar, well, the same thing. And so from this, then Z2 would be this thing. Sorry, Z2 minus 1. So that means that Z, when we write it here, Z2 equal to 1 minus E squared over 4 pi squared 2 over epsilon. And now I also have to remember that the term the term that I want to renormalize is psi bar and psi. So first of all, I have psi bar psi, which is Z2. So I have to divide by it. So this is a Zn, m, but then I have to divide by Z2, which comes from the wave function renormalization. Okay, so then this thing must be Zm over Z2 minus 1. So then I get that Zm is 1 minus, so I have to subtract this thing from this, so I get I think I should get 6, not. Well, I'll check afterwards, but it should be 6 over 8. 6 over epsilon. Because here I have 8, here I have 2. I have to subtract this. So it should be 6. That's an error, I think. Let me just write the Feynman diagram for this one, and then write the final result and some comments. So gamma 1 mu alpha beta of Q P1 P2, where I define like this. I define, now let me write this better. So this is beta P1, this is P2 alpha, this is nu prime nu, K plus P1 Q mu, and K plus P2. All right, so this this is equal to integral over the integral over the loop. Let me write the propagator for the photon in front. Delta nu prime over k squared. Now against the fermion line, so this is nu, so this is I e gamma nu, then propagator with k plus p2, so I e gamma then what did I call this? Yeah. So then the index here is mu, so gamma I e gamma mu. Then propagator, the fermion k plus p1, I p1 slash plus q slash plus n, and this is open indices. This is alpha beta again. So this is an integral of the same type as this one with open indices. There's no traces to be calculated. I can only reduce the number of gammas. But one observation is that I have now 3 propagators. I have 1, 2, 3 propagators. So I have to use the Feynman trick with 3 propagators. And I get 0 to 1 d alpha 1 integral to 0 to 1 minus alpha 1 d alpha 2. That's from doing the delta over 1 minus alpha 1 minus alpha 2 minus alpha 3. I wrote this. And then 1 over q squared plus some function of alphas, b's, and m. Okay. Yeah, now, anyway, now there's some more algebra which I detailed here in the notes, which I don't have time to explain to you, but just to write the final result here. So the final result is that the divergent part is plus I e gamma mu alpha beta e squared over 4 pi squared epsilon. So note two things. This is the classical vertex, I e gamma mu. And then this is what I said is kind of loop counting parameter in QED, e squared over 4 pi squared. And then 1 over epsilon. So then, of course, the counter term is found to be minus e squared minus this thing, 4 pi squared 1 over epsilon times the interacting vertex, which is interacting term, which is minus I psi bar a slash psi. And so we call this Z1 minus 1. And again, the wave function renormalization now is Z1 over Z2 times A. So the wave function renormalization is yeah. So, so finally, we find Z1 1 minus e squared over 4 pi squared 1 over epsilon. So again, I have to divide by Z2 because I have wave function renormalization of size as well. All right, so that was the full story of one loop renormalizability of QED. We've identified all of the divergences at one loop. We've calculated them, and we've seen that we can couple them with terms in the Lagrangian. That means that it's all renormalizable. All right, so that ends the lecture.